Okay, so in today's session, what we're going to have a look at are free body diagrams. The really beautiful thing is that I can teach you things that are weird, but easy. That sounds like a really bizarre statement to make. They're weird because you're not used to doing them. All right. And as I said to you, I find that one of the biggest problems I have with students who are older than you is they go, oh my God, that's just weird. And they just stop. They just stop thinking. So today's physics, and what we're going to look at physics today, is free body diagrams. And apart from there's an N in there, that shouldn't be there. Free body diagrams. There we go. And they're an easy way, so you can read lots of things about it. And there's words like weight and force, everything that you start getting used to hearing. But free body diagrams is a really easy way of drawing something. And what I mean by that is I'm going to start with the classic, a book on a table. All right. And if this to me, yeah, is a free body diagram, but it's too complicated. It's too much. And one of the problems in physics is when students are given a question, they don't draw it out. And we want a very easy way of drawing things out. So can you imagine trying to draw a book and a table out? It's just too much. So we either use a rectangle or a circle, it's your choice, to represent something. And that can be a car, a ball, an aeroplane. It really doesn't matter. All right. But I'm going to use a rectangle because it looks like a book. All right. So here's my rectangle. If I want to draw a table, I just draw a straight line underneath it, and that is it. I am done. Okay. So if you look at this diagram, the weight of the book is straight down. And all we do is draw an arrow straight down. Okay. This is its weight. Weight is a force because if, unfortunately, I stand on your foot, you'll feel a force in your foot. And the units are newtons. You're going to get used to this. It doesn't matter. You know, you're year 7. Just let's get used to talking about it and get used to drawing diagrams. The one thing I will say is normal people think weight is in kilograms. That is not. That is okay if you're having a chat with your friend. Kilograms is mass. But in physics, this is where I've said it a lot. Physics is a language. Science is a language. It may sound like English. It is not. So I'm talking about weight, and weight is newtons. This book is not moving. All right. So the table, which sounds really weird, is pushing back upwards. It's called the normal. And this is, apart from my little kink, these two arrows are the same size, but in opposite directions. You don't have to be exact, but pretty close. So the arrows are the same size and in opposite directions. Right. So today, what you're looking at really is just drawing the diagrams and what the words mean. And this upwards is called the normal force. So you have the weight of the book downwards and you have the normal force. Okie dokie. So now that I've done that diagram to show you the forces in a book, this is what I call we call a free body diagram. It is really easy to draw. I'm just going to talk about the normal force. The normal force is at 90 degrees, right? Let me change colour. 90 degrees. Let me do pink. Now, you should have done that in maths at some point. If you haven't, that's 90 degrees. The other word you will hear for that, let's just label this. This is 90 degrees. But there's a really horrible word that we use in maths especially. It is perpendicular. And again, I don't care if you remember this, I don't care if you can spell it, I don't care if you use it. It's just me getting you used to the language of science. So it's 90 degrees. Your contact force is always 90 degrees, not to the earth, to the surface. In this case, it's a table, right? 90 degrees to the surface. All right. Now, if you've got a slope, your normal contact force, and if I just extend it down to here, oopsie daisy, if I just extend this line, it's 90 degrees to the surface, not to Earth. No, not to Earth. Okay. Now, Here is up thrust. We did up thrust, but it doesn't matter if you remember. It is the water squishing the boat and pushing it upwards. It's called up thrust. All right. If I was going to do a free body diagram of this, I would draw a rectangle. And the boat is pushing upwards, right? And that is up thrust. Well, the person's not sinking. Right, let me just change my diagram slightly. I'm going to put it from the middle. So the boat has an up thrust. Now, because the boat's not taking off and moving up, and it's not sinking, well, its weight downwards must be the same as the up thrust. That's the weight. The units for weight are N because it's a force. Up thrust is in the opposite direction. It's an arrow. It's a force. The units are newtons. Okie dokie. Let's have a look at this person flying, parachuting. His speed is constant, means he's not getting faster and faster. Doesn't mean he's not falling. Well, I could do him as a circle. I've got the weight down and I've got air resistance up. So this would be air resistance. And my diagram is so much easier than drawing that whole thing out. Resistance, and this is weight. They're both forces. Their units are both newtons. Okay. All right, let's pick another one. Oh, this is a really weird one. I quite like this. Now, if you imagine you're hanging a picture, there is tension in the string. Can you imagine doing a free body diagram of this? Go, all right, yeah, okay, right, fine. I'm going to draw my rectangle. My weight is down. And then you start doing this, which just looks weird. And the really cool thing is, it doesn't matter which direction. So I wouldn't even draw that, right? If I went to a really simple diagram, I would do a circle, because I'm used to them. They're easy to do. My weight is down. And my strings are pulling. Oh, that's a bit big. That's a bit too small. There's a tension in them in that direction, okay? And that will do, all right? And it's really strange how you've got tension pulling inwards, but the problem is you're focused on here. I don't want to be focused on there. I want to be focused on the middle. And it doesn't matter which direction they're pulling in, as long as they're pulling upwards. And my diagram looks a lot neater. But this is a hard one. This is a really hard one, okay? The main one is this, all right? And you look at people and go, oh my God, that's really strange. All right, so I'm going to draw a circle because it's a car and it moves. You deal with each one separately. I'm going to deal with its weight. I'll tell you why I'm going to deal with its weight. The car isn't shooting upwards and isn't sinking in the ground. So these two arrows must be equal and opposite. And it's literally like looking at the book. I've got my weight down and I've got my normal upwards. That's just my normal force, exactly like the book. But I drew a rectangle and this is my weight. They're both the same size. Then I can think of everything else. Well, the car's engine is pushing it forward. And the friction is slowing it down. All right. So, about 8 minutes I've been talking. So I'm going to go through this kind of quickly. Force is a push or a pull. The units are always newtons. It's a vector, so we can use an arrow. A free body diagram, a simple sketch using a dot or a box to represent an object. And arrows to show the force acting on it. I've talked about newtons. Magnitude is the size of it in newtons. And it's a number, normally. But if it's an arrow, it's how long is your longer the arrow, your greater the force. Weight is a downward force caused by gravity. Contact force, with these two things should be touching. And resultant force is, well, if I've got a forward of 20 newtons, and let's say this is the car, and I've got a backwards 5 newtons, this is to the left, so it's minus 5 newtons, you simply take away opposite arrows. So my resultant, my overall force is 15 newtons. All right. So as per usual, you've got some easy questions. And as per usual, I expect you to read back into there. All right. Okie dokie. 10 minutes, bit too long.